2 has three significant numbers because all of them are non-zeros. The next one has only 2 because remember, leading zeros are never significant. Now the next one is a little more complex. Leading zero is still not significant, but trailing zero is significant because decimal point is shown in this number. The next one we look at only what's at the base. So it's 2 significant figures because again, decimal point is shown, so 0 is significant. Now 50,000, in this case, only 1 significant figure. So we are just saying that we are not able to determine anything, so we can only say 40,000, 50,000, 60,000. We are not able to see anything smaller than that. So only 1 significant figure because in this case, decimal point is not shown. However, when you see something like this, look at this. If you're able to see this 1 at the end, that means that you can see everything else. So all of these numbers are significant in this case. And the next one, it's also all of them because the decimal point is shown, telling you that you are able to see exactly 50,000. So the difference between this number and this number is that the first one is approximately 50,000 versus the next one, the one that has decimal point, that means exactly 50,000. That's a big difference, important difference in science. So make sure that you understand it. Now, the last number in this column would have 1 significant figure because you don't count the power, you only count the base. Here we have 2, 3, still 3, so for those two numbers it's the same, but here we are saying that we're estimating this 5 versus, in this case, we kind of are saying that we can see all 345. We don't know what's after the decimal point. And then right here, we have 4 significant figures. Now, many times we have to round. So our calculator, for example, has no clue if we are entering measurements or just abstract numbers. So a lot of times your calculator is going to show you, like if you take 10 divided by 3, it's going to show you 3.333333. So how do you know when to stop and how to round? So the rules are the first digit to be dropped is, if it's 4 or less, then you round down. If the first digit to be dropped is 5 or greater, then you round up. And let us look at the example. So 130.088, and I need to round it to 3 significant figures. So the first one is, this is my 3 significant figures, so 130. If I leave it like this, look at what happens. Then I have only 2 significant figures because my trailing 0 would not be considered significant. So to make sure that it is significant, I have to put a decimal point. And in this case, I round it down, so 130.088 is greater than 130. I round it down because my first numbers that I was dropping was 0, which is less than 4, right? And then I round down. So 2 significant figures, I would just do 130. The next one, I have to round to 3 significant figures. So 3,246.56. So I identify my significant figures, right? That would be my 3 significant figures. The first numbers that I'm dropping is greater than 5, so I have to round up. So that's going to be 325. And I need you to pay attention here. So if I put a dollar sign, your brain will very quickly interpret that 3,246 is not the same as $325, right? So what I have to do is add a 0. To keep the magnitude of the numbers the same, I have to add 0. So if you are dropping numbers before the decimal point, substitute them with the zeros. They are going to be placeholders. They're going to show just how big or how small the number is. It's not showing you. We're saying that this is not an accurate number, so we only can say for certain 325. The last one is estimated. So, but the magnitude remains the same. And if I need 2 significant figures, then it's going to be 32, right? And then the first numbers that I'm going to drop is 4, and 4 is 4 or less, you have to round down. So I'm actually going to have 2 zeros that I have to put here. The next one is 21.780. 3 significant figures is going to be 21 point, and then 7 I keep, right? But the next number, the one that I'm dropping, is greater than 5, so I have to round up. So it would be 21.8 actually. And here it would be 22, because 2 significant figures, I'm dropping my 7, that's greater than 5, so I have to round up. Now, why do I not add any zeros? That is because the numbers that I'm dropping are after the decimal point. If they were before the decimal point, I would have to add zeros to keep the size of the numbers, the magnitude of the numbers the same. But in this case, it is after the decimal point, so I can just drop some. The next number is going to be interesting. 499.999, we have to round to 3 significant figures. So if I identify my 3 significant figures, I'll see that the first number that I have to drop is 9, so that means I have to round up, right? And rounding up is going to initiate a chain of addition. So if I add 1 to the 9, it becomes 10, and then I have to add another one to the second 9. So that really becomes 500. And to show that it's 3 significant figures, I'll have my decimal point here. Now, in case of 2 significant figures, it's going to be difficult to show, right? So if I do 50, that's not correct. 50 is not the same as 500 and not close to 499. If I do 5, and plus it's not 2 significant figures. If I do 500, that's still 1 significant figure, not 2. So how can I show it? I can present it in scientific notation. So that's another reason why it is useful to use scientific notation, because in this case I can show 2 significant figures. The last example here is 1.874. 3 significant figures is going to be 1.87, and I'm not rounding up, I'm rounding down in this case, because if it's 4 or less, the numbers that I drop 4 or less, and I keep it as is. And right here it's going to be 1.9, because for 2 significant figures, if I drop 7, then I have to round up, so 1.9. Doing operations with measurements, this is where it gets tricky. So there are different rules for addition and subtractions versus multiplication and division. Although in this class we mostly are going to do multiplication and division, we are going to do some addition and subtraction for lab results, so you have to understand how to do it. So I need you to pay attention. So if you assume that all of this right here, they all are measurements, right? So then you have to pay attention to significant figures. So if you're adding them, you have to look at how many places are after the decimal point. And this is how many are going to be at the end, in your answer. So the first number has 2 places after the decimal point. The next one has 1, and the third one has 3, right? So the least precise number, so with only 1 digit after the decimal point, is going to determine how many your answer is going to have. Basically, because you don't know what's right here, what's after the 2, you are not able to say for sure anything after the second place, so the hundredths place after the decimal point. You are not able to say with certainty what's going to be there. So you have to round your answer to only 1 number after the decimal point, and that's because this was how many the least precise measurement had. So when you add, you look at the places after decimal digits, right? So for example, here we're adding those numbers. So look, we have this number has 4 places after the decimal point versus the second number has only 1. That means that your answer is going to have only 1 after the decimal point. When I did the calculations, this is the answer that I got, 6.8601. That's a calculator answer. Now, since my number right here has only 1 place after the decimal point, this is what's going to be in my answer. So it's 6. And now the first number that I'm dropping is 6, so I have to round up. It's going to be 6.9. The next one, there are 4 numbers here after the decimal. 0 number over here, so 4, 0, and then 4 over here, right? So 0 places after the decimal point, so my answer is going to have 0 as well. So the answer here is going to be 20.6912. Since we are going to have 0 numbers after the decimal point, and the first number that I have to drop is 6, I'm rounding up to 21. The next one is 1 number after the decimal point, 3 after the decimal point, and 4 over here. So this is my least precise measurement, which is going to determine how many my answer is going to have. The answer, the calculator answer is 18.8996. Since I can have only 1 number after the decimal point, and the first number I'm dropping is 9, I have to round up. It's going to be 18.9. The last exercise here is going to be 2 after the decimal point. So 2 over here, 3, and 4. This is my least precise measurement. So now if I have to do the calculations, I would get 19.3096. So since I can have only 2 numbers after the decimal point, and the first one I'm dropping is 9, I have to round up to 19.31. In multiplication and division, though, we have to look not at what's after the decimal point, but at the total number of significant figures. So the examples that's given here is that you have 4 significant figures and 1 number, and then you have 3 and another number. Since this one has the lowest number of significant figures, this is the least precise measurement, that's going to determine how many significant figures total my answer is going to have. So again, to emphasize, for addition and subtraction, we were looking at places after the decimal point. For multiplication and division, we are looking at the minimum number of significant figures, and that's going to be, how many you can have in your answer. The first exercise here is asking us to multiply the 2 numbers, and you have to look at the total number of significant figures. The total number right here is 4, versus here we have 2. So 4 significant figures, 2. So the calculator answer is 10.62045. I can have only 2 significant figures in my answer. So that's going to be this. The first one I'm dropping is 6, so I have to round up, and it's going to be 11. The next one, again, we are going to look at the total number of significant figures. This one has 5. Well, actually, I'm sorry, the previous one also had 5, right? So we have 5, 2, and then we have 4. Remember that leading 0 is not significant, right? So 5, 2, and 4. Again, the one that has the least number is going to determine my answer. So my calculator answer looks like this. 6, 7, 6, 1, 3, 1, 2, 8. So, and I can have only 2 significant figures, so it's going to be 49. The next one is going to have 2 significant figures total. The trailing 0 is significant because decimal point was shown. 5 over here and only 1, so that's going to be my least precise, so my answer can have only 1 significant figure. So if the calculator answer is 229.4425, and I can have only 1 significant figure, so the first number I'm dropping is 2, so I'm rounding down. So it would be 2, but we all know that 2 and 229 are not the same. So instead, I need to put zeros to show the magnitude of the number. The last one in this table, the first number has 3 significant figures, 4 significant figures, and 5 significant figures. So this is my least precise, right, with 3. The calculator answer is 260.45824473. So I have to round to 3 significant figures, which would be this. And since the number I'm dropping is 4, I'm rounding down, and it's going to be 260. The next set of problems is kind of the same, except we are going to use scientific notation as well. So we are doing the base multiplied by this base. So 2 significant figures here and 3 significant figures here. So if I do this, and remember that powers, when we multiply, the powers will just add together. So what I'm getting is 5.472. So I multiplied 1.2 by 4.56. And then my power is going to be 10. Negative 3 plus 7 is going to be positive 4. So the answer rounded to proper significant figures, since this one has only 2, I can have only 2 significant figures. So it's going to be 5.5 by 10 to the 4th. This is 5 because the first number I dropped was 7, so I have to round up. So, and that's my answer in scientific notation, right? So that's how it's going to look like. Now the next one is 1.2 by 10 to the negative 3rd divided by 4.56. So similar, except now this is division. So I have to do 1.2 divided by 4.56, which gives me 0.263157897. And then with my powers, I have to do 10, negative 3 minus 7, which gives me 10 to the negative 10. Since I have to round it to 2 significant figures, this is my 2 significant figures. This is going to be 0.26 by 10 to the negative 10. But this is not done yet. So now answer in scientific notation, although you would say that's already in scientific notation, that's not the proper notation. Because remember that proper notation is going to have non-zero digit before the decimal point. So I have to move my decimal point just one place to make it 2.6. But since I cannot just magically change 0.26 to 2.6 and make them equal, I have to adjust the power. So in here where I need you to pay attention, if I am increasing my base, so I'm increasing my base, my power has to decrease. And in case of negative powers, it's going to be negative 11, because negative 11 is less, it's a smaller number than 10 to the negative 10. So once again, you do the opposite. They have to balance each other. If you decrease your base, then the power has to increase. If you increase your base like we did here, then the power has to decrease. So they do the opposite. Now I'm going to delete this so that I have room to write somewhere. And now we are going to do the next one. So 8. So it's 8 times 9.987 times 10 negative 4 plus 5. So here's what my calculator is going to give me for this first operation. 79.896 by 10 to the first, right? So negative 4 plus 5 is 10 to the first. Now I have to show it to, I have to round it to the proper number of significant figures. We have 1 significant figure here and 4 over here. So I have to round it to 1 significant figure, which is going to be 80 by 10 to the first, right? And if I want to show it in the proper scientific notation, I need you to be with me. I have to move my decimal point one place, right, to make it, to have just one number before the decimal point. And if I'm making my base smaller, in this case, note that I'm going from 80 to 8, so I'm decreasing it by 1 power. So I'm making it smaller, my power has to increase. So it's going to be 8 by 10 to the second. So now let's try to mix it together. So we have multiplication problem number 3. So 0.7 times 4.916. So what's going to happen is that my calculator answer is showing me 3.4412. This is a multiplication problem, so I have to look at the total number of significant figures. I have 1 here, I have 4 over here. This is the least precise measurement, so I can have only 1 in my answer. right? So I'm going to have 3. And what about the units? If you take meter times meter, it's going to be meter square. How did you arrive to the final answer? I looked at the total number of sig figs in these measurements. And the one with the least number of significant figures determined my answer. Now in the next one, we're going to add, so 0.7 plus 4.916 plus 2.83. So in this case, it's an addition problem, and we have to look at the places after the decimal point. This one has 1 place after the decimal point, 3 places, 2 places. So this is still going to be my determining factor, but not the total number, the places after the decimal point. So it's going to be the answer 8.4, and since we're just adding, it's going to be just meter. How did I arrive to the answer? I looked at the number with the least places after the decimal. When do we not care about significant figures? When we are talking about exact numbers, when we are counting something, so we're not measuring. The difference between measurement is that you need a device to do that. When you are counting, this is something that can only be a whole thing. You can't have half a person or half a chair, right? So you only can have the whole thing. So that would be counting objects like 2 soccer balls or 4 pizzas. Or if you're using conversion factors, like we know that 12 inches always equal 1 foot. So this is not a measurement, this is not an estimation, this is just the conversion factor. We know that for a fact. Or we know that 1 hour is 60 minutes. So those are not measurements, so you don't look at the significant figures for something like this. So you can look at the examples over here. So 5 apples or 10 students, so 1 kilogram equals 1,000 grams. Again, it's not like if I measure it, it's going to be 1,000 grams, but if you measure it, it's going to be 1,050 grams. No, it's always going to be 1 kilogram is always 1,000. So all of those are going to be exact numbers. So how many significant figures are in each exact number? So you have 2, you have 3, you have 3 here, you have 2, 1, and 2. So although there's no decimal point here, because 60.0, that doesn't make any sense for chairs, because you can either have 60 chairs, or you can have 61 or 59, but you can't have 60.5 chairs. So that's going to be pay attention to this. So if you are mixing measurements with exact numbers, you only look at the significant figures for measurements. Since we're going to discuss measurements a lot in this class, we need to familiarize ourselves with metric system, or a more modern version of metric system, which is called International System of Units. Often it's abbreviated as SI. The SI system is based on a series of standard units for each type of measurable quantity, such as mass or volume. So for mass, we're, for example, going to be using grams, and for volume, we'll use liters. Although these measurements may seem unfamiliar, because we're not using them in the United States, you can think about it this way. Gram is about the mass of a paperclip, and the liter is a little more than a quart, and a meter is slightly more than 3 feet. So if you memorize those references, it would be easier for you. I moved from a country that used metric system, so I had to use and learn US measurement system. So having some point of reference really helps me. Like when I'm thinking that pound, it's 2 pounds is approximately 1 kilogram. So I can easily convert when I talk about mass, because in my head I converted to kilograms. You would have to do the opposite. Now, there are base units, like I said, gram and meter and liter, but then there are other units that are going to be representing smaller or larger quantities. And that is because imagine how many paper clips it would take to equal your body mass. In other words, how many grams it would take to equal to your body mass. You can see how awkward and big this number is going to be. Or, on the contrary, you can think of trying to get the mass of one human hair by comparing it to a paperclip. It would take a very large number of hairs to equal the mass of the paperclip. So to deal efficiently with quantities that are much larger or much smaller than one another, the SI system employs a set of prefixes that can be applied to the base unit that changes the meaning of the unit by a power of 10. So all of them are related in the power of 10. So for example, a quantity that's going to be 10 times smaller than the standard one. So let's say this is my standard, and right here it's showing meter, but it can be liter, it can be gram, it could be second. Anything that can be measured has a standard unit, right? So if we want to show something that's 10 times smaller than a meter, that's going to be deci. Something that's 100 times smaller is centi. Something that's 1,000 times smaller is milli. And now there are some things that don't have prefixes, because we can either use milli or we can skip and go all the way to micro, which is 1 million times smaller. So we are going 1,000 times smaller and then 1 million times smaller, right? Or we can, if we have to express something that's larger than the base unit, if we have 1,000 of those units together, standard units, that would be equal to 1 kilo. If you have 1 million, it's going to be 1 mega, and so on. For example, because the average person has a mass much greater than the paperclip, in fact, it would take, on average, about 70,000 paperclips to be equal to an average human, mass of the average human. You can see how inconvenient it is. So if someone asks you how heavy you are, and you are saying 70,000 grams, because remember, 1 gram is approximately the weight of a paperclip. So that would not be a convenient number to deal with. So instead, what you are going to do is you apply a prefix kilo to the base unit of mass, the gram. Kilo means 1,000 times greater. So here's my kilo. So 1,000 times greater than a standard unit. So 1 kilogram equals 1,000 grams. 1 kilogram equals 1,000 grams, right? So instead of saying 1,000 grams or 1,000 paper clips, if you want to think about it this way, we would say 1 kilogram. So we know that kilo means 1,000 of those small units, right? That's, the average person's mass would be expressed as 70 kilograms rather than 70,000 grams. If I want to present metric scale a little differently, that would help you to memorize it. So here's my base unit. And again, base unit can be meter, liter, gram. And note that those units do not have prefixes. Right? Now, if you have something that's 10 times smaller, that's going to be deci, or it can be abbreviated as the small d. Or if you have something 100 times smaller, that's centi. 1,000 times smaller is milli. And then we have two spaces, which is 10,000 times smaller and 100,000 times smaller, that don't have prefixes. The next one that we have is micro. Note that this is a Greek letter mu, and it's sort of like a U with a long trunk, if you want, in front. So letter mu, that would be micro. Now, if I want to show the difference between base unit and micro, all I have to do, I have to remember that each of these spaces is power of 10. So that would be 10, 100, 1,000, 10,000, 100,000, and then 1 million. So each of them is 10 by 10 by 10, right? So every time you're moving one more place, it's more 10. So if you count them, so that means that one base whatever it is, equals 10 to the 6 micro, for example, right? So it's 6 times multiplied by 10. Now, if you move into different direction, so if you have something that 10 times greater than base, that would be deca, and that would be dA. If something is 100 times greater, that would be hecto. And if you have something that's 1,000 times bigger, that would be kilo, so capital K. If I want to know the relationship between, let's say, kilo and base, all I have to do is think, okay, this is 10 times bigger, 100 times bigger, 1,000 times bigger, right? So 1 kilo equals 1,000 base. Note that if since kilo is bigger, you need less of them than you need smaller units, which is base in this case. One of the easy mnemonics to remember this is kittens hate dogs because dogs can't meow. So kittens hate dogs because dogs can't meow would allow you to very quickly recreate this, right? So you will remember those prefixes. And then also, I don't know, then 2 coughs or something, 1, 2, 1, 2, and then micro, that's another meow, I suppose. So try to remember. There are other mnemonics that you might choose, but you probably need to remember it because most of you are going into occupations where you're going to use metric system a lot. And the more comfortable you feel with this, the better you develop a sense. If someone tells you kiloliter or milliliter, you need to very quickly understand that one is a very large quantity versus another one is very small quantity. Also, if you work as a nurse, for example, and there is a prescription for 5 microliters and milliliters, those are not the same things, and you need to be able to understand which one is smaller, how much smaller it's going to be, and catch mistakes like this, because 5 milliliters are 1,000 times greater than 5 microliters. So if you mess up those units, you can kill someone. So you need to be able to really develop a sense for how big, how small, and be able to navigate it quickly. So let's do some problems together. So we have how many meters in 1 kilometer? So when you have a problem like this, write kilometer. So note that I put prefix first, and then I put the base unit, meter, and then meter, and put an equal sign. So you have to figure out what would be the ratio between to be equal. The one that is a greater unit, which is kilo is a greater unit, put 1 next to it. And then count how many places it takes to get to whatever you are trying to compare it to. In this case, it's a base. It doesn't have a prefix. 1, 2, 3. So that's going to be 10 to the third, or it is the same as 1,000, right? Because 10, 100, 1,000. How many decimeters? So you put decimeter. In a meter, 1 meter. So we have meter. 1 meter, right? So we put 1 meter, it's a greater unit, and plus it's asking you about meters. And deci, so now you have to look at how many it takes. So this is my meter, that's my base unit, and deci is right next to it on the right, so 10. So it would be 10 decimeters that equal 1 meter. The next one is going to be how many megameters in 1 meter. I need you to pay attention here. So mega is actually going to be 1 million times greater than kilo, than base, 1,000 times greater than the base. So 10, 100, 1,000, 10,000, 100,000, 1 million. So mega is 1 million times greater than the base, right? So, but here it's asking you to do slightly different. It's asking you 1 meter, how many megameters would it equal to? Well, so if mega is 1 million times greater than the base, then it's going to be 10 to the negative 6 megameters. So in other words, think about if you have something that's very, very large, right? And it's asking you to compare the small part of it to this whole large part, then it would be the small one divided by the large one. So in other words, it's going to be 1 megameter divided by 10 to the 6 small base units, which are meters. So that will equal to 10 to the negative 6. In problem 4, you have to compare 1 meter to millimeter. So I identify my meter, identify my milli, and it's going to, we are going to move 10, 100, 1,000. So 1,000 or 10 to the third. 3 powers of 10 is 10 to the third millimeter. So 1 meter contains 10 to the third millimeters, really small units. On this page, you have to do a practice problems. I'm going to do a couple of them with you, and then you can continue. So I suggest that you have this kittens hate dogs because dogs can't meow. And then remember 2 more spaces and then micro, right? So that would help you navigate it. So if it's asking you to compare a kilometer and a meter, so what you have to do is find your kilo and your meter, which would be a base, right? And again, you recognize bases because they don't have prefixes. So none of those have prefixes, so that must be base. Okay, so we have a base, and then the one that's larger, put next to it 1, and then count how many powers of 10. So it's 10, 100, 1,000. So it would be 10 to the third, or you can write 1,000, it's up to you. So the next one I'll do, for example, this one. So this would be comparing millisecond and centisecond. So I have to find, this is my milli, this is my centi. So the one that's larger, and the larger units, so larger units are moving this way. So centi is going to be larger, so I put 1, and then there is 1 place, so it would be 10 milliseconds in 1 centisecond. So please complete the rest on your own.